A new look at Alpha Centauri. This follows on from Once Around Alpha Centauri, which is a video that I did, I think it was about 4 years ago now. So this is somewhat updated since then with the latest news. So the constellation of Centaurus, the Centaur, is a very large area down in the southern sky, approaching towards the south celestial pole. You can see the area marked out with the blue boundary, and taking a bite out of it is Crux, the Southern Cross there, very prominent constellation. Down at the bottom left, indicated by the little pink arrow, we have Alpha Centauri, the brightest star, and next to it, Beta Centauri. Now, we'll look at Beta in another video, but we're going to concentrate on Alpha Centauri this time. It came to attention of astronomers a very long time ago. In 1689, it was identified as being a binary star, and it was actually only the second such binary system to be identified. And there's a photograph against a relatively bright blue background, in fact, of the two components of this binary system. These days, our telescopes are able to track them, and we can see the diagram of the orbits as they both orbit around the common center of mass in fairly elliptical paths. In 1976, the separation between them was at its maximum 22 arc seconds, so easy to see. In 2016, it had reached the minimum separation down to 4 arc seconds, so very much closer together, but still observable with reasonable astronomical equipment. Now, in addition to being noted as a double star, in the 1800s, people were starting to track the positions of stars against the very distant background, and they noticed that Alpha Centauri was changing its location quite rapidly, a large proper motion, as it's called, as it proceeds on its path around the galaxy and we proceed on our own. The line of sight to it changes against the background. And in the 1830s, 1832 and 33, astronomer Henderson was able to use the Earth's orbit around the sun as a baseline, the parallax method, and figure out the distance. And he was so surprised with the large deviation that he got, corresponding to a very nearby location, that it didn't immediately publish. In fact, it took him some 6 years before he had the courage to follow up and publish the value that he got, which corresponds to about 4 light years. And makes this the record holder. The modern data is 4.37 for the main Alpha Centauri star, by far the closest star system to the sun. And in fact, we can now track these things very accurately indeed, and these are the close approach trajectories of various stars that are moving relative to the sun, and it shows that at the moment, where the vertical blue dashed line is, the record holder is currently the Alpha Centauri system, actually in the form of one of its components, which we'll come on to, called Proxima Centauri. But other stars will swing towards the sun and away again as their relative position changes on their paths around the galaxy. You can see Barnard's star there, which is currently in second place, is going to come less than 4 light years away. Ross 248, Gliese 445, and so forth. And so Alpha Centauri will not always be the nearest star to the sun. But as I said, this is a multiple star system, and in 1915, using blink comparator photographic plates, Robert Innes was able to notice that a faint star in the constellation of Centaurus was moving from position to position, and we have a modern animation from 1985 to 2010 there of the star moving against the background. And he was then able to use parallax method, again using the Earth's orbit as a baseline, and measured the distance as 4.24 light years, bringing it to a new record slightly closer than the Alpha Centauri system, Alpha Centauri AB, the double star that had been discovered a couple of hundred years earlier. So where are these on the sky? Well, I've got this lovely photograph of the sky there with the Southern Cross, Crooks, and Alpha and Beta Centauri shining against the background of the Milky Way stars there. And inset, you can see the current 4 arc-second separation between A and B. And then slightly offset from that, you can see an inset with Proxima Centauri, which is actually 2 degrees away from the AB pair. And there was a big question mark over this. Was it really part of the same system? Was it anything to do with them? They seem to be at roughly the same direction in roughly the same part of the sky, but that 2 degrees separation is quite significant. In fact, I've got another parallax photo for you here, this time not taken using the Earth's orbit as the baseline, but a much longer baseline of 50 Earth orbits, 50 Earth radii, so 50 times 150 million kilometers. And this was taken using Earth as one end of the baseline and the New Horizons spacecraft out in the Kuiper belt, well away from the sun now, long gone past Pluto and past Arrokoth and out into the outer reaches, but able to photograph Proxima on the same date as the Earth and give us a very accurate rendition of the movement and thereby pin down that distance very accurately indeed, because we got this much longer baseline. Now, until 2017, it was uncertain as to whether Proxima was in fact gravitationally bound to the main Alpha Centauri AB pair, or whether it was merely passing by. But measurements with the Gaia spacecraft have shown that Proxima is in orbit around them, but it's taking over 500,000 years, 550,000 years to do one orbit, shown in the diagram here with the very bright Alpha Centauri and the tiny little faint Proxima down at the bottom right, and the great big long elliptical orbit. That varies from 13,000 AU to 4,300 AU. And at the moment, the star Proxima is at apastron, which means it's at the far point from the central region. Periastron would be the close approach in its orbit, but it's at apastron, the most distant point at the moment. So we have these 3 stars, a pair orbiting each other quite closely, and a more distant component in a very, very long orbit. And physically, this is a nice diagram that shows how to compare them against the sun. We have the sun on the left, Alpha Centauri A, called Rigel Kentauris, the foot of the centaur, and Alpha Centauri B, its slightly smaller companion, goes by the name Ptolemon. This is because in ancient cultures, the Greeks referred to A as Rigel Kentauris, the foot of the centaur, and Ptolemon comes from the Persian scholars and referred to it as the ostriches, so a completely different constellational arrangement. But this is unusual because we don't usually give the B star in a multiple system a proper name. We just refer it as Alpha Centauri B. But this was felt to be so important that they decided to adopt the name Ptolemon. And then Proxima Centauri, a little red dwarf star, much smaller by comparison, and Proxima meaning nearby. So we don't find another nearer one. I'm pretty sure we won't. You can compare the sizes of the stars all the way against larger stars like Sirius, a hotter, whiter star, down through Alpha Centauri A, Rigel Kentauris, the Sun, Ptolemon, and then some of the smaller stars there. I've done videos about some of these, Captain Star, and of course Proxima at the bottom there, right at the extreme end of the red dwarf range, really. Go much smaller and you're into the failed star territory of brown dwarfs and giant planets such as Jupiter. So a few facts and figures. Rigel Kentauris A is a G2 class star, a yellow dwarf, temperature 5,790, a little bit hotter, just a few tens of degrees hotter than our sun, and just 10% more massive. It's that extra mass that causes it to burn fuel faster and increase its radius and be hotter. And therefore, the total output over the larger surface area at a higher temperature comes out to be 150% of that of the sun. So this dramatically shortens the life from around about 10 billion years of the sun down to 6.8 billion years before Rigel Kentauris will run out of fuel. And that gives it about 1.8 billion years left, because it's roughly 5 billion years old. When that happens, it will swell up to form a red giant and then puff off the outer layers as a planetary nebula, leaving behind a small white dwarf star about half a solar mass. The sun will do very, very similar things in another 4.5 to 5,000 million years. Ptolemy, a little bit smaller than the sun, 90% the mass, a little bit cooler, a few hundred degrees less. And that smaller surface area and lower temperature leads to the fact that the total output radiating away from the surface is about half that of the sun. And so it's going to live roughly twice as long, 20 billion years. Being around 5 billion years old, it's got plenty of time left. It's only a quarter of a way through its life. But its evolutionary destiny is very similar. Red giant, planetary nebula, small white dwarf. Proxima, this is just 12% the mass of our sun and a 50,000th of the total solar output, something like that. And that's going to give it a lifetime of 2 trillion years as it gently burns through the fuel. And eventually we think it will form a helium white dwarf. Of course, won't be around to see it. And no red dwarf star of this mass has got anywhere near reaching the end of its life, even if it was formed right at the very first star of the universe about 13 billion years ago. It will have just got nowhere in terms of consuming its fuel because of the expected lifetime, 2 trillion years. Now, these stars are all rotating, and it's very interesting to see that the rotation speeds of the stars seem to get slower as they are smaller. It is the big stars that spin faster. I guess this is because the angular momentum of all the material that fell in to make the star is conserved, and you've got a lot more mass in the larger stars crammed into a fairly small volume. And the result of that is that the star has spun up to a higher rotation rate, conserving the angular momentum. So you can see the numbers there. And those spins lead to magnetic fields in the conducting plasma of the star. And this, of course, leads to magnetic storms or star spots, sunspots on the sun, star spots on the stars. And when we look at the stars, Rigel Kentauris A seems to be asleep. It seems to have gone into a coma, a deep Maunder minimum, as we would call it, because the sun did this a few hundred years ago. It ceased to produce sunspots and became very quiet for a long period of time, while A seems to have done that since about 2005. And Ptolemy B, that's still magnetically active, still cycling away, producing rashes of sunspots, and doing so on a cycle of 8.2 years. The sun does the same thing. We have an 11-year sunspot cycle. We're a little bit bigger and we spin a bit faster in just 26 days. So these processes all seem to be related and make sense. Now, I mentioned that the stars were about 5 billion years old. It's actually most straightforward to age stars in the red dwarf category because they are fully convective. They're fully stirred. All the material is stirred through the core and out to the surface. This is one reason why they live so long, because they are able to use all their available fuel for fusion in the core. And it also means that all the helium that they started with, plus all the helium that they have made, in their life gets distributed through the star. And so we are able to look at that and get one data point that gives us a clue as to how old the star is. But we also know that these little stars don't make any of the heavy elements. They only manufacture helium. They don't make carbon or any of the later steps. So any carbon or oxygen that we see in the spectrum of the star was there when the star formed. And that acts as an anchor point for the signature of just how old the universe was when the star formed. That tells us how much helium there would have been when the star formed as well. And comparing that with how much we now see and the power output of the star, we can constrain the age to a very good value. In fact, 4 significant digits here, 4.853 billion years. It's less difficult to do, less straightforward to do with the larger stars. The stirring process is not quite so straightforward. And so we are less certain. Rigel Kentauris A also dates at 4.85 billion years. We're not able to be so accurate with that one. And for Ptolemon, an orange star, it's very tricky. And the estimates are somewhere between 5 and 6 billion years, which seems to be older, but that might be wrong. And it's possible, indeed probable, that all 3 of these stars were formed at the same time. Certainly, it seems very plausible that A and B in their tight orbit were formed together. But some people have suggested that actually Proxima is not part of the same family and has been captured much more recently, hence its really wide separation and that very, very slow orbit. Indeed, if it encounters gravitationally with another star system, it's entirely possible that Proxima will get removed and sent on a completely different future direction. So we shouldn't really use the age of Proxima as the sole guide to the age of the other 3, and it would be interesting to try and pin that down some more. But if we look to the future, the stars will evolve, and the larger they are, the shorter lives they have. So Rigel Kentauris A will swell up to a red giant first and turn into a white dwarf. And then later, in a few billion years' time, maybe 20 billion years, Ptolemon will also swell to become a red giant. Now, because the orbits of the 2 bring them within 11 astronomical units, the distance of Jupiter, more of the material from the outer layers of Ptolemon becomes at risk of being drawn away by the gravity of the A white dwarf and pulled across onto it. And this mass transfer could reduce the mass of Ptolemon in its late stages and increase the mass of the white dwarf. But if you do the sums, the white dwarf from Rigel Kentauris is likely to be about 0.6 solar masses, and there just isn't enough mass in Ptolemon to add to that to take the whole total over the Chandrasekhar limit, the limit at which a white dwarf star would explode, creating a type 1a supernova. So this mass transfer may well strip Ptolemon down and boost the white dwarf, but it's not going to result in a giant solar explosion. I'm not sure that we'd be worried if it's in 15 billion years' time anyway. So the question then is, do these near neighbor stars of ours have planets? And the answer is yes, because in 2016, we discovered Proxima b, lowercase b, for the first discovered planet. And I don't know what happened to A, but they don't start from A, lowercase, for some reason. And this turned out to be very Earth-like. It's about the same size and mass, maybe a little larger and a little heavier than the Earth, and in a very tight orbit, 0.05 astronomical units. So that's very much closer even than Mercury is to the Sun. the orbit just takes 11.2 days. But at that distance, given the low power output of the red dwarf star, you're going to get a reasonable amount of heat arriving, and we'll talk about that in a moment. 3 years later, Proxima C was discovered in a wider orbit, a Mars-like orbit at 1.5 astronomical units, taking 5.2 years to go round. The longer period is because the central star is of lower mass, and we can apply Kepler's laws of planetary motion to work out and be very precise about the orbits and get very precise measurements of the masses of the central star using that method. And then also in 2019, Proxima D was discovered as an inner planet orbiting around in just 5.15 days. And this is a low mass planet, just 0.29 of the Earth's mass. So very low weight indeed. Small Mercury-like planet, but closer in by some significant margin. So if we then just look in detail at Proxima B, discovered 2016 of August by the radial velocity method, where you don't look for the planet, but you look for the radial Doppler shift of the light from the star, getting bluer and redder alternately as the star wobbles back and forth, pulled towards and away by the rotation of the planet around it, pulling in different directions. So it oscillates as the planet goes round, and the oscillation period, well, that's the orbital period of the planet. And from the size of the oscillation, we can work out things to do with how much mass the planet probably has. And we get an answer, but it's a little tricky because we haven't seen the planet and we don't know whether it's orbiting in a plane that we are looking at edge on or much nearer face on. If it was perfectly face on, we wouldn't see the effect at all. But the more face on it is, the higher the mass would have to be to cause the same line of sight deflection of the Doppler shift from our point of view. Now, at the distance that this seems to be of 0.05 astronomical units from this relatively cool star, we can use maths and calculate how much heat is going to arrive and what that's going to do to the temperature. And it seems to bring the temperature up to minus 39 degrees C baseline. Now, that baseline is without any greenhouse effect. And in fact, if the Earth had no atmosphere at all, then its baseline would be minus 20. So we would be frozen up solid. It's the atmosphere that brings it up from minus 20 to a much more tolerable plus 20. And that extra 40 degrees is very helpful. What we don't need is for that to become 50. And so if Proxima B has an atmosphere as well, then it would be able to bring it up from minus 40 degrees, minus 39, up to perhaps a livable temperature. And if the planet is a little bit bigger than the Earth and has slightly stronger gravity, maybe it could do that. There is the issue that it's probably tidally locked in the same way that the moon keeps one face to the Earth due to the effect of the tidal forces. Maybe Proxima is so close to its star that it too would become tidally locked. And it would be very, very interesting to be able to understand its rotation period on its axis rather than just the orbital period as well, and try and understand that. And that's ongoing work at the moment. Being so close to these red dwarf stars is not necessarily an advantage. There can be some very strong solar winds and flares, and we also suspect that Proxima may get blasted by X-rays from its star, about 400 times more intense than the Earth suffers from. So this habitability, some people question. Just in terms of a size comparison, we've got the sun, so big it won't fit on the screen at the bottom right, the little Proxima Centauri red dwarf star, Jupiter and Saturn for comparison, and Proxima and the Earth. And so we're saying really that Proxima is pretty much the same size as the Earth. We're fairly sure about the mass, and we have some idea, therefore, about what it might be made of and its likely density and size and so forth. But these are not precise measurements yet. But the problem, as I said, with being too close to your star, especially a red dwarf star, is that red dwarf stars can be rather rowdy during their first couple of 100 million years. They still end up giving off quite a lot of solar flares and so forth, but actually during the first 200 million years, they are very active indeed. And that would increase the thermal and radiation output and move the habitable zone where water might exist out beyond where Proxima is, because today it's right slap in the perfect position to be able to have an atmospheric greenhouse effect to bring it up to a livable liquid water condition, but only if it's got some water left. And the problem is that if the star was too violent to begin with, it may have fried it to a crisp. So I'm not sure if I really sign up to this theory, because with the Earth was formed out of accreting a lot of material together. And to begin with, certainly for 200 million years of its existence, it would have been a lava ball. It would have had such enormous amounts of heat from radioactive materials and from the kinetic energy of bombardment that their surface would be several hundred degrees in temperature and too hot for liquid water. Any water would have been boiled away and might have been in a very steamy envelope around the planet, or might have been lost completely. And the theory goes that it was only after the Earth had cooled down several 100 million years on that comets and asteroids brought more water to the Earth and delivered all of the oceans that we see today. So the idea that the stellar winds could have blown away all of the volatile materials during those early times on Proxima, I'm not sure it really matters, because it would have been so hot on the surface with all that molten rock everywhere and lava that the volatile materials would have been up in the atmosphere or indeed lost and had to be replaced. So I'm not sure. Now, the other thing is, if the planet is a little bit more massive than the Earth, it would hang on to those gases in its atmosphere better. If it had a spin and a magnetic field from an iron core, it could protect itself from a lot of the solar wind, as our planet currently does. So there are arguments to and fro on both sides. But the recent news is that measurements seem to be pointing towards water being present. Indeed, some suggestions are of a global ocean, so a water world. And there have even been suggestions that they've observed lights on the night side of Proxima b. Are those lights artificial lights? Are they, I don't know, some chemical process, glowing volcanoes? We're not sure. Watch this space. As soon as we find out a definite answer to that, we'll come back with another update. So moving on beyond Proxima b, we have Proxima c, the second planet to be discovered, and that was in 2020. A super Earth planet, 7 Earth masses, an orbit of 5.2 years, but at that orbital period and the corresponding distance from the red dwarf Proxima Centauri, the temperature is going to be minus 234 degrees C. So that's the equivalent to the temperature on the surface of Pluto. This is very cold indeed, and not a habitable world at all. Now, it's been directly imaged, and the inset down at the bottom there shows a little tiny point of light with a blue ring added round it that they say is Proxima c. I'm not quite sure how they identify that as being significant compared to all the other dots in the photograph, but I'm assured that that is correct. and it's sufficiently bright that there is some evidence that it has a ring system. Now, that's disputed, and in fact, the whole existence of Proxima C has been called into question recently. And this is a problem that seems to happen with a lot of exoplanet discoveries, that we find that there are pulsations and rotations of the star itself that mimic the effect of the radial velocity wobble of various periods of planets. So we're still in some debate on this one. Slightly more certain is the third one, Proxima D, an inner planet in this Mercury-like orbit, a third the mass of the Earth, just whizzing around every 5 days. So interior to Proxima B, and it should be a lowercase d. I'm sorry, that's an uppercase D on the screen there. Lowercase letters for planets, uppercase letters for stellar components. Anyway, right on the inner edge of the habitable zone, and here's a plan showing B, C, and D orbiting around Proxima. And you can see that B and D are very close in, and the disputed Proxima C in a much wider orbit. What has been discovered and imaged on the right-hand side here is a dust disk, rather like the Kuiper belt. It's between 2 and 4 astronomical units out from Proxima, so well outside Proxima's habitable zone. And this could be the realm of a lot of comets and ice worlds, all forming another Kuiper belt, as well as a lot of dust, or it could be just dust left over from the whole star and planet formation period. But what about the other 2 stars? What about planets for Alpha Centauri A and B? Well, they orbit each other quite closely, just 11 AU apart, and that's well inside the size of the solar system. So you would have 2 stars whizzing around each other in the realm where you might want to put your planets, and that's probably bad. But you can calculate spheres of influence, so-called Hill spheres, or around each of the 2 stars where their gravity is dominant and the gravity of their more distant neighbor is irrelevant. And this leads to there being some stable orbits. You either have to be close to the A star or close to the B star inside a couple of AU, so inside the sort of size of the inner solar system. But that's fine, because if we're interested in Earth-like planets orbiting around Alpha Centauri A, you would want to be at about 1.5 astronomical units, and maybe if you were orbiting around B, you would want to be closer in, and that's shown in the green zones, the Goldilocks zone, the habitable zone around the star. And here we have it illustrated slightly more technically. So Alpha Centauri A, you want to be in that 0.8 to 2.4 AU band, and possibly where the dotted line is. And then for Alpha Centauri B, a corresponding slightly smaller green zone. So definitely possible to put planets in those zones. Now, we haven't found any yet, although in 2021, it's possible that we found a super Neptune orbiting around star A at 1.1 AU in a 360-day long orbit. Very, very Earth-like parameters, just slightly further from the slightly hotter fire and taking a year to go round. And constraints on the mass here, Alpha Centauri AB, or Candidate 1 as it's called, C1, well, we're not certain, but round about somewhere between 9 and 35 Earth masses and 3 to 7 Earth radii. So pinning this one down would certainly be very helpful. And in fact, searches being undertaken with James Webb Space Telescope to try and pin this down. It's a great instrument for that, for finding these planets. Its infrared capability comes in extremely useful. Now, Tollyman, well, this is perhaps an even better candidate, but we haven't found any at all yet. There was one announced in 2012, Alpha Centauri BB, and this again was determined to be an artifact of the data analysis. So, is there one? Well, 2013, another possible transit event this time was observed with a planet just 92% of that of the Earth in a 12-day long orbit, though. That would be extremely hot indeed. And if that transit is repeated enough times, we'll be able to hone in on that and figure out whether there is such a planet. But again, it's a bit too close. Now, again, both of these seem to have dust disks, Kuiper belts, asteroid belts around them. For star A, it's just outside the habitable zone at 2.8, and likewise B, it's at 2 AU. So rather like our asteroid belt, just out beyond Mars, really. In fact, 2.8 AU is the orbit of Ceres in the solar system. So this is very much like an asteroid belt. But it seems to have a lot more of the dust left over, 10 to 100 times more dust than we have in our solar system. So if we take that idea of the Hill sphere, the sphere of gravitational dominance around a body, and we have a think about the Sun and the Alpha Centauri system as a whole, separated by that 4.24 light years between the Sun and Proxima, and we work out the values that we get for RH, the Hill sphere, we can plug in the numbers, and you have to take a third of RH, the radius, is equal to the distance between them divided by 3 multiplied by the cube root of the mass ratio. That's the formula. And plugging the numbers in for the Earth, that means anything within 0.76 light years of Earth is, or in fact the Sun, is dominated by the Sun in terms of gravity. So 0.76 light years is the radius of the Sun's dominance. Do that for the Alpha Centauri system. We have to add up all the masses of all three. So 2.1 for the total, made of 1.1, 0.9, and 0.1. Add those together and plug that into the formula, and we get a ratio coming through at 1.59. So if you're within 3/4 of a light year of the Sun wins. If you're within 1.6 light years of Alpha Centauri dominates your gravitational destiny. And if you're somewhere in between, well, then there's no clear winner. And so objects in that gap could well go either way. And I've seen a recent study that has shown that there are a tremendous amount of small, tens of kilometer sized icy bodies floating around in that area. Better watch out if you're planning to take a trip to Alpha Centauri. There's a lot of things to hit, and traveling at half the speed of light, that would hurt. And so really just a little local map with the Sun in the middle, Alpha Centauri and Proxima there just over 4 light years, Barnard's star at 6, and then a couple of groups of brown dwarfs, in fact, come next, just over 6 light years away. And we have the Oort cloud in the middle, and that corresponds roughly to the size of the Hill sphere, that 3/4 of a light year gravitational dominance by the Sun. Anything in there is really in orbit around the Sun. Go any further, then actually the gravity of Alpha Centauri starts to become comparable. So if you're in that intermediate gap between around about the 2 light-year mark, it's not clear that you would follow the sun around in orbit at all. So we have this neighboring star system right next door with a family of planets around Proxima and possibly planets in the other systems as well. We've seen that there's probably a liquid water ocean there, and even that there might be lights coming from the night side. I'm fascinated to know if that gets to be confirmed. And we received a radio signal. The Parkes telescope in Australia was looking at flares on Proxima, and hitching a ride on the side of it was the Breakthrough Listen project, taking a feed of the radio signals and analysing them. Now, the aim of the project is to look at 1 million stars across a wide range of frequencies. But back in December of 2020, it was announced that they had found one signal, having sifted through millions of candidates and thrown them all away. There was one left, BLC1, Breakthrough Listen Candidate 1, and it seemed to be coming from Proxima. They had originally determined that it was not an earthbound signal, that it was not a natural signal because it had a very narrow frequency range, 982.002 megahertz, very precise indeed. There was a rising pitch Doppler to it, suggesting it was accelerating towards us. There was no modulation, no message encoded in it. So what was this? A beacon, a dial tone, a carrier? And it lasted for 3 hours and then stopped. Well, we still haven't got to the bottom of this. There has been a paper published that suggests that 982 megahertz might well correspond to a Japanese mobile phone, and that somebody might have been driving in the direction of the observatory, and that had got into the equipment. There were thousands and thousands, in fact, millions of signals that were detected in the equipment and eliminated as false positives because they used an off-axis detector pointing in a different direction. And if that too picks up the same signal, then your signal is from somewhere nearby on Earth and is interference. And this signal, there was no detection in the off-axis. So we don't know. And unfortunately, it hasn't repeated despite many listens. So this may have been a one-off. It may have been radio frequency interference. But we live in hope that one day we'll be able to answer some of these questions. And here is just a nice little rendition of what the sky would look like if you were standing in an observatory on the dark side of Proxima b, looking up at the night sky back towards the sun in the top right, Sirius, Betelgeuse, and some of the familiar stars of Orion, but some changes because of your slightly different aspect. So that's the latest that we have on our nearest neighbour, and we seem to be homing in on the answers tantalizingly close to some of these things. But thanks very much for listening, and I'll leave it there for now and come back when there's any more new news.